Hello and welcome. My name is Julian Linke, and my colleague Anneliese Kelterer and I am presenting you today the paper with the title Towards Automatic Annotation of Prosodic Prominence Levels in Austrian German. And yeah, my colleague Anneliese starts with the presentation now.
Thank you. Prosodic annotation is one of the most difficult and time-consuming tasks when creating a speech database, and that's why we would like to develop a tool for the ongoing prosodic annotation of Austrian German in the Graz corpus of read and spontaneous speech on the basis of as little manual annotation effort as possible. And our second aim is to examine which acoustic features contribute to the perceptual prominence in Austrian German on the basis of the labels used by the annotators. We define prosodic prominence as the property by which linguistic units are perceived as standing out from their environment by prosody. Languages rely on different weightings of acoustic cues to create perceptual prominence. Usually a combination of F0 variation, duration and intensity and other acoustic cues. For German there have been, studies have found different weightings of acoustic cues. So some studies found that F0 was more important than duration, or pitch accent was more important than either duration or F0. Other studies found that word duration was more important than F0 and intensity, or that force accent parameters, which are a combination of duration and spectral emphasis, are more important than pitch accent parameters. For Austrian German, it has been found that duration and spectral tilt were more important correlates of syllable prominence than F0 movements. There are several tools around for automatic prosodic annotation. Some of them use acoustic features in combination with lexical, syntactic and context information, and some only use acoustic features. However, the ones that only use acoustic features, they either classify syllable prominence or they use features extracted from the syllable to classify word prominence. And what we would like to do is to develop a tool that classifies word prominence exclusively on the basis of acoustic features extracted from the word domain without the need for syllable annotation or other linguistic information, which would necessitate more extensive and time-consuming manual annotations before the application of the tool. In this study, we used two read narratives from the Graz corpus of read and spontaneous speech. It was annotated by 3 annotators for 4 prominence levels, 0, 1, 2, and 3, which correspond to no prominence, weak prominence, strong prominence, and emphatic prominence. Here you can see the kappa values, Cohen kappa values, which indicate the inter-annotator agreement. Our training set consists of 2,919 word tokens from 197 utterances, and the test set contains 269 word tokens from 47 utterances.
Okay, thank you, Anneliese, for this introduction. So I'm going to talk about the second part of this presentation, and which is about the materials and the methods we used to solve this classification task and get a prominence detector somehow. So I want to say again that the main idea here is to really look just at the acoustic features to classify prominence. So in our case, we had 84 features based on F0 and RMS, and 12 features which are based on durational characteristics. And we solved this classification problem in the sense of supervised learning. So we had the prominence levels from the annotators as labels. And in the first method, we did a binary classification task just with a decision tree. And in the second method, we introduced another class, so another rating, and solved this with a random forest. So let's start with the first method. as you can see, we have a really simplified method with just two classes. In the first case, we have the prominent class, which has the label PR here, which unites all prominence levels from 1 to 3. And on the other hand, we have a non-prominent class, NPR. And the motivation behind this first method was just to ask the question, is it possible to detect prominence? Can we do something with it? And yes, we can say we find a highly simplified model in this case, which is a decision tree just with a depth of 1. That means we have just one feature, in this case the word duration, which gives us sufficient results. So in comparison to a lot of other more complex algorithms, we can say this is enough to solve the task. And here you can see the results illustrated as confusion matrices. On the left-hand side, you see the results of a validation set. In this case, we took about 10% of the training set to validate the data and also change our parameters. And on the right-hand side, you see the test set, which is an extra set from other annotators that we use to evaluate our system. And yeah, if you look at the left matrix, you see we have a bisymmetric matrix, so on really good results. On the main diagonal, you see the recalls, so 87% of the non-prominent words are really categorized as non-prominent words. On the other hand, prominent words are also 87% of prominent words are also recognized as prominent words. In the case of the test sets, the results get even better when we look at the prominence rating. There we have a recall of 93%. So what can we say after all? That in this case it's really easy somehow to separate prominence. We just need to look at one feature, which is called the word duration. In our case, the decision tree just asked the question, is the duration less or equal to 0.25 seconds? And then we say it's a non-prominent word. On the other hand, we also looked at the F1 scores, because the F1 scores somehow combine the measurements recall and prominence and give a good representation of our prominence detector. And as you can see, non-prominent words have a F1 higher than 90%, and prominent words have a F1 higher than 87%. So we can, in the end, say, okay, we can detect prominence, and the advantage here is, of course, when we think about the annotation process, it simplifies the process, because we could say that we just give the prominent words to our annotators, and they have afterwards just to evaluate if it's prominence level 1, 2, or 3, and the non-prominent words are really detected before. So nevertheless, we also stepped further and said, okay, what happens if we don't unite the prominence class into two classes, and we say, okay, we have now class 0 as a non-prominent class, and class 1 as the prominent rating 1, and class 2 as the higher prominent rating 2 and 3 combined in this case. And here we decided to take a random forest. In this case, we had 1,000 decision trees with maximal depth. And in the end, we can say that in our feature selection or in the ranking of this random forest, that 5 features are enough to solve this problem. And those 5 features are the duration, the F0 rail range, the F0 range, the RMS rail range, and the RMS range. Yeah. The results you can see on this slides. On the left-hand side, you see the confusion matrix of the validation set, on the right-hand side of the test set. And yeah, what we see on the first side, non-prominent words are, like before, also good detected as non-prominent words. And the prominence class 2 is also at 82% with a recall. But when we look at class 1, we see there are a lot of confusions. So in the case of the validation set, 33% of class 1 is detected as class 2 and 21% as class 1. On the other hand, when we look at the test set, this somehow shifts in the right direction of class 2. So here we have 52% of class 2 detected at class 1. So this somehow also makes sense, because when we look at class 1, also the annotators have some kind of problems to really say, is it class 1 or is it class 2? So these ratings are not so easy somehow, and our detector is representing those results also. So when we summarize also those results, we can say, okay, in the end, we just needed 5 selected features to be sufficient with a 3-class problem. Here, non-prominence class 0 has a F1 score higher than 85%. So in this case, it's like in the decision tree. We can also detect prominence with this model and non-prominent words with this model. And when we look at the weak prominence class, as you saw before in the confusion matrices, we have a lot of confusions. So in case of the validation set, we have 51% F1 score. In the case of the test set, 34%. And when we go even further to strong prominence, it gets better again. So we can say, after all, good recognition is possible of class 0 and class 2. So we can also detect prominence, but we have further informations about class 1 that we have here some kind of a confusion, but that is also information which is in the sense of linguistic knowledge important to know. So.
The random forest also gives us more information about the relative weighting of the acoustic features for prominence in Austrian German, and it showed us that word duration was more important than relative and absolute F0 range, which were in turn more important than relative and absolute RMS range. Even though there are other studies about prominence in German, most of them are not directly comparable to our study because they either classified syllable prominence or they examined word prominence, but on the basis of features extracted from the syllable or even from the stressed syllable. One study that is comparable to ours in terms of methodology is Arnold, Möbius and Wagner, and they also found similar results to ours. So in their study, word duration was more important than the maximum F0, which was more or less as important as intensity. The advantages of our approach are that it captures very late peaks that are located outside of the stressed syllable, but which are very important for prominence perception. And it also indirectly captures segmental reduction phenomena outside of the stressed syllable. Now we look at the distribution of the data in the whole training set in red and in the test set in gray. And we can see that for duration, the values increase with increased prominence. Here we can also see in the test set in gray that the whiskers of classes 1 and 2 don't extend that far into the lower values as in the red figure. Which might be a reason why the recall of the prominent class in the decision tree was even better in the test set than in the validation set. The duration of less prominent words is shorter because they are shorter words, often they are function words, but the local speech rate also shows that speech rate increases with decreased prominence. So even though speech rate was not significant in our classification, the speech rate shows that less prominent words are pronounced faster. We see a similar pattern for the F0 range and the RMS range as for the duration. The values increase with increased prominence. In the random forest, class 1 was more often misclassified as class 2 in the test set compared to the validation set. And this might be explained by the distribution of the RMS range here. So if you look at the distribution of the RMS range in the test set in gray, it resembles more the distribution of class 2 in the training set in red. A reason for this different distribution might be that the reading styles were slightly different in the test set because it did not only include narratives. To conclude, the F1 scores showed that the binary classification task of the decision tree had a better performance than the tertiary classification task of the random forest. Our study showed that the classification of non-prominent versus prominent is easier than the classification or the distinction between different levels of prominence, so between classes 1 and 2. And the random forest showed that word duration is a more important feature for prominence than F0 range, which is in turn more important than RMS range for Austrian German. This tool will be used in the semi-automatic annotation of the Graz corpus, and in the future it will also be implemented in a prosody-dependent ASR system. Thank you.
Thank you for listening.